Hello, everybody. Okay, this is a little mini lecture on objective two, or observation two. I want to start out with latitude and longitude. There are basically three coordinate systems we deal with in this class, um, all, exclusively within the observation area, and pretty sure we do not test over it. But let's just talk about latitude and longitude coordinates and coordinate systems in general for just a few minutes. A coordinate system is used in order to locate a place on a object, be it a graph or a map or the globe. And we use latitude and longitude as the coordinate system for the Earth. And latitude latitude represents the angular distance north or south of the equator. North is positive, south is negative, and it consists of great circles. I'm sorry, check that. It consists of parallels. You can see parallel circles here, and the lines of latitude are parallel to the equator. Now longitude represents the distance east or west of the prime meridian, which runs through Greenwich, England. And so you can, by your longitude coordinate, you can tell how far east or how far west you are from that point. Now latitude, the way in terms of the words, I always think of latitude, I always think of ladder when I think of latitude. And I see these these parallels as crossbars on a ladder, and you can climb either north or south. Whereas a longitude, I think about the length of them. The longitudes are the long ones. They run from the North Pole to the South Pole. Okay, a second coordinate system that we talk about is the local coordinate system, or local grid, and it consists. This particular coordinate system is used for your own personal use. You wouldn't share these coordinates with somebody in England, for example, because this coordinate system is unique to your position. The reason for that is it's based off of your zenith. And if someone's standing next to you and they look up, their zenith is going to be slightly different. So if you had a really precise and accurate uh, measuring system, then the two coordinate systems would not agree. But the zenith, remember, is the point directly over your head. So when you look straight up in the sky, that's the zenith. Now the meridian is the line that runs from the north point to the south point through that zenith. So that's your meridian, and that meridian for any particular location determines whether or not it's AM or PM. In the morning, the sun is to the east of the meridian, and we call that antemeridian. In the afternoon, the sun is to the west of the meridian, and we call that postmeridian. And so that's the AM and PM. Now there are two coordinates in this system. One is the direction, also called azimuth. And azimuth is just a compass heading or compass direction, and the altitude, which is the height above your horizon, your angular height above the horizon. And so those are the two coordinates that we have. Now, in terms of correlation, the altitude would correlate to the latitude, because it determines north or south. It determines the height above the horizontal plane that you're standing on. And the direction, or azimuth, would correspond to the longitude. It determines your east-west position. Okay, The third coordinate system that we talk about is the celestial coordinate system, also known as the equatorial coordinate system or coordinate grid. Now, let me back up a little bit and say a couple of words here about the local um, coordinate system. Now, if you take a look at this, the local coordinate system or local coordinate grid forms a cage through which you look when you look out into space. It is fixed to the ground that you're standing on. So this coordinate system will rotate with the Earth. And since the Earth is rotating always, then the coordinates of any celestial object or celestial body will change moment to moment if you're using the local grid. And therefore it's almost completely useless in terms of research and communication with other people. So instead of that, we have what was created was the equatorial coordinate grid. And what that is that's a celestial sphere that surrounds Earth. And it has, the coordinate system has a celestial equator, which is just a projection of the Earth's equator onto the celestial sphere. It also has a north celestial pole and a south celestial pole. And it has a couple of other things that we will take a look at. What I did want to show you is that the celestial equator and the ecliptic are not the same thing. The ecliptic is the path of the sun, the apparent path of the sun in the sky. Actually, what it is it's a projection of our orbital plane onto the sky as well. Both of those are true. And you can see that at the summer solstice, the sun will be down here. At the equinox, it'll be over here. And at the June solstice, it'll be here. And vernal equinox, it'll be here. And those are just basically how that works out. So the celestial sphere, or the celestial coordinate system, uses two coordinates. It uses right ascension and declination. The origin of the coordinate system is a point in the sky on the horizon, if to an observer who is standing on the equator, and that point is defined as the point that the sun can be found at on the vernal equinox. So on the vernal equinox, the location of the sun at that point, that is an observer on the Earth's equator, that would be the point of zero right ascension, zero declination. Now, if you move around that circle on the celestial equator, the distance east and west, those are marked off by great circles of right ascension. And if you go up or down, north or south, then those are marked off by parallels of declination. So a declination goes with a longitude or altitude. A right ascension goes with latitude or azimuth. Now these two coordinate systems are independent of each other. Because the celestial coordinate system is not fixed to the Earth, but instead is fixed to the stars don't move around in that coordinate system during the night. Clearly, the moon or sun do because of the speed of their the the movement. No, check that. They do not either. The sun's location and the moon's location do not change in the celestial sphere very much during the day. They change more than a distant star would. but they don't. It's a pretty constant. But the point is that the fixed stars, the celestial objects which are far away from us, they're on the celestial sphere. They're painted. It's a reasonably permanent coordinate over hundreds and thousands of years. They do migrate, so you have to rebalance the coordinate system. But those are fixed, and the Earth spins underneath the celestial sphere. So the coordinates of a star are fixed, and they don't change from day to day if you're using the equatorial or celestial coordinate system. Now that's different than the local coordinate system, which changes because of the rotation of the Earth. Now what I wanted to show you here is that the two systems, the blue here, the dark blue, is the celestial coordinate system, okay? And if we had where's our zenith? There's our zenith. Here's north, and here's south. So the two coordinate systems, if you're at the North Pole, the two coordinate systems align, because when I look straight up at the North Pole, then I'm looking at the North Celestial Pole. I'm looking at Polaris. And so my meridian will align with the right ascension line, the appropriate right ascension line, and the two coordinate systems just merge. As you change your latitude, however, since the equatorial coordinate system is fixed relative to you, is fixed relative to the stars, and the local coordinate system is fixed relative to you, the two coordinate systems separate. That is, there's an angle between the two of them. And that will be important for us to explain some of the rise and set angle calculations that you do in this observation. You'll see that further. All right, let's take a look at just measuring I'm going to go the sunrise of the sun, the rising of the sun. And the way we do that, we'll push sunrise. I'm going to stop it. The book tells us to speed it up to 300. I'm going to locate the sun. Oh, come on, stop. I am going to stop. I'm going to locate the sun. And here's the sun. Now it's February, so the sun is moving from its far easterly position back towards the east, when it will, at the equinox, at the vernal equinox, the sun will be over the east point during rising. Okay, now what I'm going to do is I'm going to select the sun here, and then I'm going to right click, and that will open up a menu, and I'm going to go down here and I'm going to click local path. Then I'm going to go ahead and run the time forward, and we're going to watch the sunrise. However, I'm also going to do one other thing. I'm going to take away the sunshine, okay? So I'll make it dark so that we can see what's going on. And now I'm going to go ahead and allow the sun to rise. Okay, there you go. The sun's rising, and the system is drawing a nice line for you from which you can measure. And now stop the system. Okay, now put your protractor here. Put the origin of the protractor right here, and put the horizontal, please, just on top here so that it's flat. And then make sure that the 90-degree mark is straight up. We could, let's see if we can catch a local coordinate. If you move the local coordinates so that one of them is straight up and down, that will help you orient your protractor so that the horizon and this are perpendicular. Okay, then you put it in there and you measure that value. And I've measured this value several times today because I've done this talk several times. I've had technical troubles. And I find that the angular, the rise angle of the sun on today, on February 3rd, is about 30 degrees. And so that's what it is. It's about 30 degrees here today. Now let's go to, I'm going to turn the sunlight back on. And I want to take you up to the North Pole. And let's go there quickly. And let's see if we can't find that sun again. All right, there she is. Sunrise, February 3rd at the North Pole. Does that make sense to me? Oh, I didn't take us to the North Pole. Let me do that again slowly. Okay, to change your location. What you do is you come up here to the viewing location area of the menu. You drop down. Use the drop down menu. You select Other. And now we wanted to go to the North Pole, so our latitude and longitude here is 90 degrees at the North Pole. I put in 0. That's the equator. So we're going to go to 90 degrees, which is the North Pole, and we're going to go there. And we're going to see that the sun is way down here. It's below the horizon because we're still in winter, and the sun has not yet reached the equinox point. So let's change our date. Let's change the date, and let's go to the 30th of March. And we can now see the sun. All right. Let me clear the local path because we brought it with us. And then I'm going to go ahead and re-enable it so that it's fresh. Next thing I'm going to do is start it up, and we're going to watch the sunrise. Okay, we are standing at the North Pole. We're standing on a spinning globe. And the sun is directly over our equator. And it turns out that we can see to the equator, if you look out far enough, the projection of the equator, we can see that far, but we can't see down below the equator because the Earth is in the way. And what we notice here is that we're sitting on top of a globe that's spinning, and since the sun is over the equator right now, it doesn't rise at all. What it does is it goes horizontal to the horizon. Now the angle between that straight line that goes from here to here and the straight line that goes from there to there is 0. They're collinear. They stay on top of each other. The angle is 0 between those two. So what we just found out was that the rise angle at the North Pole is 0. And what part of this assignment is teaching is there is a relationship between your latitude and the rise and set angles of the sun. And if we think about this, we're at 90 degree latitude. If we take 90 minus 90 degrees, that is 90 minus our latitude, we'll get 0, and that's the rise angle. So 90 minus your latitude will give you your rise angle. We'll talk about why it's not working in Olympia in just a second. Let's take a look to see if it worked at the equator. So we'll go back here, and we will go to the equator. And now we'll go to sunrise. Here, sun is over here. And let's see. I've learned from previous experience that that particular line is the um, previous path and what it would take. Okay, now let's enable it again, the local path, and let's let the sun rise. Now what's happening is we are observers standing at the equator of a spinning globe. And if you were to think of yourself tipped over and rolling through space, then when you roll through space, the objects on the celestial sphere are going to see it go straight up. And we'll get rid of the sunlight so we can see it better. Okay, it goes straight up. So the angle here between the sun's path and the horizon is a right angle. That's 90 degrees. And it looks like we've got at least there's a comet out there. So that's 90 degrees. Now the rise angle here is 90 degrees. The latitude at the equator is 0. So how do we calculate rise angle? 90 degrees minus the latitude is equal to our rise angle. So 90 degrees minus 0 is equal to 90, and we have our rise angle. Now the thing of this is that this does not work when you are at mid-latitudes. Okay, it doesn't work when you're at mid-latitudes. At mid-latitudes, it will work pretty well on the day of the equinox. Okay, so for example, if we were to go to sunrise again, there's our line for sunrise. Okay, and if we were to measure that line, we would find out it's approximately 42, 43 degrees to the horizon, because we're basically at the vernal equinox. The sun is over the equator. But if we were to change that we were to change that back to February, let's see. We change that back to February, then this angle became 30 degrees. And like I said, the formula is 90 minus your latitude. So the latitude of Olympia is what? The latitude of Olympia is 47 degrees. Okay, 47 degrees is the latitude of Olympia. So we would expect 43 degrees to be the angle of rise if the formula worked every time. But what I found earlier today is that that rise angle is closer to 30 degrees on February the 3rd. And then it approaches 43 degrees when you get to the equinox, because at that time you have the situation where the sun is on the over the horizon. So for this particular assignment, it makes it difficult to come up with the right formula that we're looking for, because the measurements we make for our own location don't match what they quote should, because we're not on the right day of the year for them to match. Now, I mentioned before when I showed you those pictures that if we were standing right on the, let me go ahead and enable the equatorial coordinates, and we will get rid of well, we'll just leave it there. Um, we can see the equatorial coordinates here. The red are the equatorial ones, and the white lines are the local coordinate system. And if we let it move a little bit, you can see that the stars stay fixed with the equatorial coordinate system. That was a satellite that just went by. Satellites move around. And I'm going to turn off the sunlight. You can see that the stars are fixed relative to the equatorial coordinate system, but they move relative to our local coordinate system. See how that works? Okay, since this is the case, you can also see that these two coordinate systems are at an angle with each other. And if we were at the North Pole, let's quickly run up to the North Pole and see how it looks. All right, let's quickly go up to the North Pole. We said that was 90 degrees north latitude, and we'll quickly go there. I'm going to remove you can see that the two coordinate systems lie parallel to each other. They overlie each other. They may be offset because of the numbering system, but they're parallel. Especially you can see here the parallels, the lines of declination and altitude. Okay, so they line up when you're at the North Pole. If I go back to Olympia, and now I'm looking north, let's go back here and look east. You can see that they're not lined anymore because you changed your latitude, and because you changed your latitude, that also changed the local coordinate system. It came with you. But the celestial coordinate system didn't move, and so the two coordinate systems separated. And at the bottom of page 15, the book talks about a method that you can use which allows you to measure more precisely the rise and set angles of the sun using that method. Now, if we go and look west, okay, I'm going to go look west. We don't even need the sun for this. What they say to do is they say come up here and select the angular separation tool and come to the horizon and pick out the local meridian that's right through the west point. Okay, then draw the angular separation tool up, and there are two numbers. One is the angular separation between the origin of the line and the current point of the line, and the other one is a position angle. That position angle is the angle between the two coordinate systems. It is also the angle between the direction you're pointing now and the direction of north. So, for example, if I rotate this, see my right ascension lines, you notice are parallel, and the north celestial pole is over here. And if I point in a direction which is parallel to those lines, you can see it's very tough to get exactly parallel, but there it is. Oh boy, and I had to let it go. Choke under pressure. Okay, so anyway, so there you go. Um, we'll have that the position line they were pointing towards. We're off by about a degree, but so this line here is pointing towards north, the north celestial pole. Okay, and this line here is not. It's pointing in the direction of where west is, and it's about 43.2 degrees. We're about 43 degrees. Remember that our position is 47 degrees latitude for Olympia. 47 plus 43 is 100, or as 90, and so that works. And what you're actually measuring is you're measuring the angle between. Here, let me get rid of the horizon, and maybe we can see a little better. We're measuring the angle between the two coordinate systems. All right, so this angle down here would be a good one. Let's do the adaptive. Okay, so here's that one points north there. That goes to the north celestial pole. Okay, then we have this coordinate here, which is our west point, which runs from our west through our zenith to our east. And so the two coordinate systems are offset by this angle here. And that angle there we measured to be 43 degrees. So that's what you're actually measuring when you measure this. And that angle is equal to the rise angle when on the vernal equinox, the sunrise angle on the vernal equinox. So that's how you do it. This will always be the right rise angle because it's much more easily measured. If you have questions, please contact me and I'd be happy to answer them. I'm going to re-enable horizon. I'm going to turn the sunlight back on. I'm going to turn the equatorial off, the local meridian off, and I'm going to take a look at the stars. What is this one right here? Omega Tauri. Wow, that's a big star. Oh, it's a moon. Oh no. Oh, wait a second. Is that our moon? No. Oh, it's Jupiter. That's what it is. So Jupiter is out tonight. It's in the western sky. We have another bright star here. That's Betelgeuse. That's part of the Orion. These are the seven sisters. They are known as the Pleiades. And anyway, it's fun to go out and look at the stars. If you familiarize yourself with some of the bright stars here, and then go out and take a look at the sky, it's a lot of fun. Anyway, give me some questions if you have them. I know that that some of you struggle with this topic, so good luck.